Now we need to discuss how to construct physical simulations. Physical simulations can quickly become fairly long programs. We're going to follow a plan which helps us think about how to work through these things. First off, you need to write down what it is that you're expected to get out of a particular simulation. Is it a single number? Is it a function? Is it a plot? Know what you're aiming at. The second step is to write down all of the equations and known quantities and constraints. You want to know all of your starting variables, all of your physical constants. You want to be thinking about the different available methods that you have. Are you going to use finite difference or analytical differentiation using SymPy to solve this problem? As a third step, you now begin to write code. Once you've gathered all those pieces, you can write your code in short segments, and you can make sure that each section yields an intelligible result. It's a good idea to begin with a small problem rather than trying to create the entire simulation at once. At the end of writing and testing code, you should make sure that your final result is in the correct form. If that's a plot, a number, a report, whatever you end up with at that point. Now, we are going to consider a particular physical problem. Imagine a cup falling off the edge of a table. And let's say that that table is 1 meter high. We want to describe its path, or its height, over the time until it hits the ground. We have 3 different approaches available to us. We can use an analytical equation if one of them is available, and in this case, for this problem, we can write down an analytical equation. We can use a finite difference equation if we don't have that available, or we can do what's called integrating the equation of motion. If we use an analytical equation, what we've done is we've looked in our physics textbook and we've found a formula that describes what's going on in this situation. We can say that height y as a function of time t is equal to y naught, the initial height, plus v naught, the initial velocity, which will be 0, times t, plus a by 2 t squared. And a is acceleration due to gravity, negative 9.8. So it starts at a height of 1 meter and it drops to the ground, but there's an additional constraint on our simulation, which is that the cup can't go into the ground. So yt must be greater than or equal to 0. This actually makes our code a little bit more complicated once we think about adding that constraint. Let's look at solving this analytically first. We could solve this analytically using SymPy, or we can solve it analytically using NumPy. Here we've opted for a NumPy-based solution. You can see that I've set up the parameters of simulation in what I've called state variable initialization. Essentially what I've done is I've written down the things I know and the things I need to have available, such as the time at each time step and what my starting and ending time are. I've written down the equation y as a function of t and a, but it's calculated as a single expression, y equals 1.0 plus a by 2 times t squared, because NumPy gives me that flexibility. Then I have this interesting for loop. It loops over the entire range from 1 to n plus 1. It checks to see whether or not that value is below the ground, and if it is below the ground, then it simply forces it to rest on the ground. When that cup or glass falls and it hits the ground, it stays on the ground. We're not simulating bouncing. We're not simulating it cratering into the earth. It hits the ground and it stays there at y equals 0. And then we're going to go ahead and plot that result as a blue line. So it takes a brief moment to solve. And you can see here that with our x-axis being time t, and our y-axis being height y of t, we can see that we start at the top and we fall in a paraboloid shape until we hit the ground. There's an interesting feature at the bottom of this where you see this little jag around time t equals 0.45. What's happening here is that we're simulating this problem at discrete steps, but we're drawing a straight line between adjacent points. And sometimes this leads to edges knocked off of things where we'd expect a tighter simulation. If we were to plot this with the points instead, this would become more apparent to you. We'll do that with blue circles now. And now you can see what's happened is we are simulating this fall correctly, but because of our hard enforced scenario at a certain spacing in time, it looks like we're jogging over unnaturally. In the scenario where we don't have an analytical equation available, or for reasons of speed we decide not to use it because it may be cumbersome to calculate, we can use a finite difference method to solve our problems. In fact, on the homework, this is what we're going to expect you to do. In this case, we can write down our expressions like dy dt is the definition of velocity with respect to time. This is approximately equal to the difference in my y values over the difference in my t values. And if I rearrange everythyn, I can write an expression for each subsequent time n plus 1 purely in terms of the preceding time, yn, and then the known spacing tn plus 1. I can do the same thing for my change in velocity with respect to time. That gives us a constant value a. We know that. So we can enforce that same kind of relationship. And then I can put in all these particular constraints for n equals 0. So our starting velocity is 0. Our starting position is 1. We know the acceleration due to gravity. We have the same constraint. And I can build this into a finite difference simulation. This code, in many respects, looks similar. The top has our parameters of simulation and it has our state variable initialization. I'd like to draw your attention to a few features here. We're still setting up time going from starting time to ending time with n plus 1 data points. We are setting up an array y and an array v ahead of time that are full of zeros. Because it takes a lot of time to append something onto the end of a list computationally, it's frequently more efficient to pre-allocate the entire array and then fill it as you go on. This also has the added benefit of not needing to change values once we get to the zeros when it hits the ground. We say y0 is our initial step, and then we write a for loop over each of our time indices. First, we calculate the change in v. vi is equal to the previous time steps vi plus a times delta t. We do the same thing with y. We check our condition that y should be greater than or equal to 0 and enforce that. And of course, we also zero out our velocity, should that be the case. We're going to plot this with y as a blue line and v as a blue dashed line. Now there are some oddities in this particular scenario because of that. You can see our blue line is again a paraboloid ascending till it hits the ground at about the same time as what the analytical equation gave us, and then it goes to 0. Our velocity is linearly decreasing, which makes sense because it's constant acceleration. But then it very suddenly gets reset to 0 because we've enforced that hard boundary constraint that when we hit the ground, we stop accelerating, nothing else happens. There is in fact a discontinuity when something hits the ground. So this makes sense from a physical standpoint as well. Numerical integration, or numerical quadrature, can also be used to solve this problem in terms of what we would call the equation of motion. So in this case, we have a statement for y, which is the integral over time of v as a function of time. Since we know v is a function of time in terms of acceleration, we can write out this entire expression. Here we're using tau as our variable of integration to keep t, which is effectively a constant for a particular value of y, from changing. Here we're going to use quad from scipy.integrate as we've done before. We're going to define our velocity as our integrand, negative 9.8t. We're going to pass that into quad. We're going to grab the 0th component because quad is going to return to us a tuple. We're going to add 1 for our initial height. This is like adding the constant when you do an indefinite integration. So we're going to add that constant in to define our initial condition to satisfy that initial height. And now this tells us at a given time t, so at 1 second, what our y position would be. The disadvantage of this method is that you only get the end result for a given interval. And in this case, it's also difficult to impose external boundary conditions. If you want many intervals, you'll need to have a list and a loop to put this together. So in this case, we're going to solve for each time t. We're going to add that into our list y. We're going to convert that to a NumPy array, add 1 for our initial condition, and then plot it as a series of blue points. So in this case, it gives us that same curve that we've seen before. It doesn't enforce the condition. In practice, you'll see all 3 of these methods used: the analytical solution, the finite difference method, and numerical quadrature. In 101, I will always specify to you which one of them I expect you to use, or I will tell you to simply use one, select one, and give me the correct answer based on what you know. Modeling has a few more considerations. For instance, how would you make the cup bounce? Let's say it's a rubber cup and I want to watch it bounce. It still wouldn't go under the ground, but I need to figure out how to model that physically. So the easy way to do it is to reverse the direction at the ground and include a decay factor for each time it bounces. You could model this rigorously, but in practice we'd probably just say, okay, it bounces back and based on the material it retains 30% of its kinetic energy. How would you include lateral motion? You'd have separate x and y positions and velocities also as functions of t. Now, numerical modeling is very cantankerous in many ways. If I were to show you these 2 graphs of a ball bouncing, with the x-axis being t and the y-axis being height, could you tell me which one of these is physically correct and which one is not? If I lay them on top of each other, does that make it any easier? It really doesn't. One of the challenges with numerics is that you can arrive at a lot of answers that are sort of plausibly close to reality, depending on the assumptions that you make. In practice, of course, a ball doesn't bounce forever, but at some point absorbs enough of the kinetic energy and its internal degrees of freedom that it simply rests on the ground, right? It's not a perfectly bouncing object forever. It will eventually settle. These equations don't exactly do that. They never really settle out. And so minor changes in assumptions about how simulations are constructed can lead to divergences in outcome later on. For instance, if I asked you to count the number of times that a ball is bouncing, each of these 2 lines would give you a different number when you get to a particular time step. So it's important to note that while numerical models can give us a good idea of what's going on, they're not going to give us completely precise information about the world around us. And that's fine. Most of the time we're not employing them to do that. In solving the homework, I've made certain assumptions about the numerical problems that you need to solve. You need to hew to these assumptions as closely as possible, because otherwise you'll end up with a simulation that looks like the purple line, the magenta line, whereas I'm asking you to solve something that looks like the blue line. So that's something to keep in mind as you work on this. Numerical work is frustrating and rewarding at the same time because of these ways that it can go wrong, these ways that it can diverge from the same answer in all cases. But ultimately, it's the tool that we use to get the best picture of the physical world around us as we model structures and fluids and everything else that's going on mechanically in this physical world that we inhabit and we manipulate as scientists and engineers.